You know, there's a lot. Okay. This is a sketch of the reservoir production model. And we basically have a gas reservoir with NW number of wells, each producing with the same rate. The rate given by this rate equation, which is including both the reservoir and production tubing pressure losses. We have a very simple material balance with no support of water inflow, ignoring the effect of non-ideal gas behavior. And we have the A constant reflecting reservoir properties and the B constant reflecting the tubing diameter for practical purposes. All wells are assumed to be identical, and that assumption, though it may seem dramatic, if you look as you drill the wells in reality, if you look at those wells, and for each well, look at the A as you're drilling up the number of wells, what you'll find is that you'll get a good well, you might get a little better well, you'll get a little less well, maybe you'll get a dog, and then you'll kind of move along like this. Maybe in general you get poorer quality the more wells you drill. But what you can show is that for a single reservoir unit without barriers, flow barriers, that a single well approximation, as we're doing, a single average well, in fact, is almost identical to taking the running average A, okay, of all the wells, kind of a cumulative average, which would look something like this. Okay, and what you'll see is that the more wells you drill, the better this becomes a good assumption. And in reality, what we're looking at this point is the average performance after all of the wells have been drilled out. So the more wells you add, the better this general assumption is. It's actually quite a good assumption. Early on, you have a lot of excess deliverability from this well, and then you lose some. Okay, you see what's happening is that you're so making the assumption of some average A is really quite an okay, acceptable assumption. Let's see. Are there any other questions about this reservoir production model before we move on to the processing? Because what we're going to do now is take and add the next modeling, which will be taking the gas stream and creating sales products. Okay? We're going to try to do economics on this integrated model project. So we need to do economics, and to do economics we need to know what products we're selling, and we have to have models for the main cost items. The main, there's a general infrastructure cost, maybe it's a platform or whatever. There are individual well costs. There are costs of, let's say, expensive processing, and there's a number of perhaps other costs that I haven't included. But we need to bring in some major cost items that are coupled to the variables in this integrated project. So now we're going to basically take the field stream and enter a processing facility where I believe it's two products are generated. Okay, sales gas, and we'll just call it natural gas liquids. And these are being extracted by some kind of low temperature cryogenic dew point controller equipment. It's very expensive equipment. It's very energy intensive equipment. And so the processing is going to be more or less efficient depending on the temperature of what we'll call the dew point controller. That will be the main process variable. An assumption is being made that the incoming stream composition, that it's a wet gas reservoir, meaning that the composition of the gas is invariant or constant with time. Okay? So the flowing well stream composition is assumed to be invariant. And it's this, the modeling of this here, that is in the second sheet called process. Okay? Sales gas and NGLs. So Oklahoma, they don't spit out the gum, they spit out, chewing tobacco. I could just put a bucket over there and I could just, you guys would be in the the zone of danger, but okay, so that's basically the products, and this would typically be calculated by a model like HISYS or some kind of flash calculations, some program that does flash calculations where you separate the composition stream into 2 or 3 products. Any questions about so far? This is a lot easier than the course I teach because you don't have to do any Ratchford Rice calculations. So I've come up with a very empirical model where the first thing I say is that of this incoming stream, there's 10 mole percent of which can be extracted as the natural gas liquid. Okay? If we have a dew point controller unit operating at its maximum capacity, then we can extract out 10 mole percent of the gas stream as a liquid. Yeah? The efficiency of that extraction process is controlled by the temperature in the dew point controller. The maximum temperature would be, let's say, something like the initial separator temperature. So let's draw a picture of our process a little bit, a little more detailed. Let's say we've got some initial separator here, separator pressure and temperature, and let's say this is for some reason very high, 80 degrees C. And then we're going to take this gas out, and essentially we're saying that the liquids are nil. So it's a wet gas. There's very little surface liquids being processed out. Maybe some water, slight amount of condensate. And then we send this gas here through the dew point controller unit. It's another flash calculation. And from here we get our natural gas liquids. And from here we get the sales gas. Okay. Now you could easily change this problem if you want to make it into like a gas condensate. You could easily do that. But if you bring in a gas condensate where there's a significant amount of condensate coming out here, then that amount would vary as a function of average pressure, meaning time. Once the reservoir goes below the dew point, the amount of that condensate would be changing with time. So we would have to introduce kind of a time variable process. And I didn't want to do that in this project. I wanted to make it simple, relatively simple. But you could try to introduce a condensate where you bring out a product. You could have another mole fraction of condensate, maybe let that be constant, independent of the surface processing. But for this problem, we're going to make it simple. Now, the maximum, if we have 1 kilogram mole coming in, the maximum coming out here is 0.1 kilogram mole. Okay? And then that's going to be multiplied by some kind of efficiency factor for the NGL. Efficiency factor. And that goes from 0 to 1. And it will be equal to 1 at a dew point controller temperature of minus 40. If we run the DPC unit at minus 40, we'll get all of that out. And if we run it at 8 degrees C, we get none of it out. Okay? But I want to introduce a nonlinear dependency here. So I've come up with a, this is a gas to NGL conversion factor. And you can see here that if I go from 80 degrees to minus 40, then this F NGL, which I should have called F instead of E, F NGL goes to 1 when we have minus 40. And if we go between 80 and minus 40, what's in the middle? 20? Okay. Then we're only getting out 12.5%. Go to 0, we get out 30%. So the function for that, the empirical function for that, is a model 1 minus 1 minus F6, which is this normalized temperature. So let's look what the normalized temperature is. That's the dew point controller temperature minus the minimum temperature divided by max over min. So we have basically the NGL amount is equal to the, let's say, the molar rate of the stream coming in times this 0.1 Z NGL. That's the total potential NGL times this efficiency factor, F NGL. And F NGL goes from 0 to 1 and is equal to 1 minus the normalized temperature to the power of n. And normalized temperature is defined as the actual dew point controller temperature minus the minimum over the dew point controller max minus min. Okay. So what you can see as a consequence, you have to get closer and closer to 40 let's say minus 20, before you start seeing even half of the efficiency coming forth. So you have to get relatively cold temperatures to get a high efficiency. The shape of that curve, I would think, should probably let you just plot that in Excel. Probably looks something like this. Well, it's something like that, I think. So we got down to minus 20 and we were up around 60%. So, okay. Now, obviously, that's a Curtis empiricism, so whether that's at all realistic, I don't know, but I suspect there's something to it. This gas to NGL conversion converts standard cubic meters of gas to liquid NGL cubic meter. Okay? So, actually, the volume of NGL in cubic meters per day is actually such that we can take the gas field rate, which is the same as moles in a way. This all would be in standard cubic meters per day gas-like volume, and then multiplying by this NGL conversion factor. And the NGL conversion factor would simply be something like it would be something like 23.64 down here, and then times the molecular weight over density of the NGL, I think. And the NGLs are probably C2 to C5 components, some kind of. That's the process model. Are there any questions about that? Any? Now, how we would actually come up with such a proxy or approximate model would be to work with the HYSYS engineers, the process engineers, put the streams through, ask them to run a series of cases where you change the temperature of the dew point controller and look and see what kind of NGL liquid volumes you get out. That's simple. Just ask them to run 4 or 5 cases, you fit it to some equation, you're done. Okay? Stainer, you look mystifyingly confused. Too simple? Okay. So that's basically the process model. So we've got these numbers that we can eventually change if we want to change the type of dew point controller and the range of temperatures, the exponent, the amount of the. So you can change to a whole different gas, leaner gas, richer gas, properties of the NGL components, this process efficiency, and the range of the dew point controller temperature. All of these are main first-order variables in such a system. These are our intermediate kind of calculation. Now, we have to adjust the actual gas production volume from the previous reservoir production. We have to convert that to a dry sales gas. Dry gas, by that I mean it's dried of NGL, so it's the remaining sales gas. Okay? And this shows of the well stream gas coming in, what fraction is actually being sold as a dry gas. So we're losing 5.8% of the well stream. We're losing that as the gas product, but we're gaining that as a liquid product, which has a much higher value. Okay? So we get a lot more money for this 5.8% sold as an NGL liquid than we would have if we sold it as a gas. Okay. And these numbers, some of these are tied. Now, when we talk about integrating models, okay, in Excel, what does integration mean? It means linking to another sheet with the other model. That's easy, okay? You just go over and you point to the cell. It brings with it the sheet name. That link is easy to make. That kind of link is not easy to make when you've got HISYS and you've got Eclipse and Sensor. Those things become the technician nightmare of making all of those links, integration links, work. Okay? Here, it's simple. So in connecting a reservoir simulator to HISYS, the technology of what is here a point and click away might take weeks. But once done, it's done. Okay? Once that communication is done between the reservoir simulator and HISYS, then that's basically done for this particular project. But it does take an effort to do that. More or less a one-time investment. Let's see. I think that's the only link. I think that's the only integration upstream. It's basically fetching the volumes of gas coming from the reservoir production model. Any comments or questions about that? Now, if I were, since we're a little bit into teaching you guys good Excel working ethics, okay? If I were given a spreadsheet like this, then I would be interested in seeing this relationship between efficiency and temperature. I mean, I would want to see it because and then I would want to plot the 5 or 6 points from HISYS on that curve and do that exercise. So what basically we can do is that we can have something like this, and this is the FNGL. Start there, and that's 10. We're not going to do anything very sophisticated. I'm just going to go down to, that's not what we wanted to do. There we go. Okay. And I'll put the intermediate in here, just so that'll be that minus that fixed address divided by actually this is not right. Yeah, that's better. That minus like that. So I fixed the address to these two cells here, and then the the row numbering will be allowed to vary as I copy that cell down. Give it a couple of decimals. And luckily it goes to 1, to 0. And then we've got this function 1 minus this to the power of 3, which we have to fix the address and bring that down, and then mark the two columns that we want to plot. Insert chart XY, symbols and lines. Next, x-axis is dew point controller in degree C, and that's the efficiency, DPC efficiency. F NGL. I like to have both grids. Always do this as a new chart, and this is our MGL efficiency. Okay, and then this is my procedure. I click. The first thing I do is I click on the outside here, format the plot, change to black, white on the inside, and then on the outside change the font to 16, because then it's ready to be copied into a report. And of course we need to have our bounds to be what's representative, and 20 is probably okay. And then we'll have this going down to minus 40. And make this 16. Okay, and then change the symbols to circle. This is something that when I was at Stanford 30 some years ago, that we couldn't turn in a plot that wasn't made properly. That means written like this with the symbols, the certain symbols types, certain type of lines. Now it's a lot faster and easier, but it takes me 10 seconds to turn it into something that would have made all of my professors very happy. Keeping them happy, that was half of the trick. Okay, and there we've got this okay, so that's took about extra 30 seconds to turn it into a plot that you can copy and paste into a journal as part of a paper or report. That's all it takes, about 30 seconds. Okay, if you don't go to 16-point font, you can't. You have to be young to see the figure, and this way you can copy and paste it in, and even reduce it in size and still see it. Efficiency greater than 1, not usually there. And so. And then what I would actually, yeah. So if you, to paste it, you go to the outside, you have it marked the entire thing like that, and then copy it, and then we can go into, we go in and make just an extra sheet here, like that. Now when you paste it in, either to Word or PowerPoint, you do paste special in this enhanced picture file. Don't ask me why. Don't ask me to try anything else. And I don't know what about 2007, but this is what you want to do. Okay? And there it is, full life. For PowerPoint presentation, it's wonderful. in terms of size relative to everything else. In the report, you can make it half the size. You can still read it, even a quarter size, with the 16-point font initially. Copy, paste special, picture enhanced. Don't use the default. Okay. So then if you're interested in studying, for example, well, let's use something linear. Of course, you know what that's going to look like. You know. And if you want to get extreme, of course, that's okay. So you can study, and if you, like I was saying, that if I was really working on a project, then what I would do is I would have basically these two columns and this would be my ISIS results, something like that. And then you might have a couple of cases where you do, 40 and 25 and 0 and minus 30, and then they don't give you any more. Okay? So you go in, you get 4 points from them, you're happy. You put the numbers in there, you plot it against the function, and you may find that, well, it looks like we need to have something that looks more like this. Okay? And you have to figure out a functional relationship that will give you that. Okay? Because maybe the points look like that. Okay? Integrated modeling, that requires some interaction. Without the integration, we're talking about building a proxy model. We have to work with the HYSYS people. Now, ideally, you'd like to have the reservoir simulator integrated with HYSYS so that you could check the results and compare against your simplified proxy model, right? You'd like to have this proxy model that runs like that, but you'd like to be able to say, oh, well, let's check and see what the results are if you run the full simulator, the full HYSYS and everything, as a control of the approximations you're making. Okay? Now, there's a significant cost associated with this guy here. Okay? There's a big cost associated with that. Both operational cost, because it's consuming energy. So you're losing gas sales because it's burning the gas to run the refrigeration unit. But you're gaining a lot of added value. That 4, 5, 6 mole % that you can sell as a liquid has 7, 8 times the value per mole. 7, 8 times the value per mole to sell it as a liquid than as a gas. So in the economics, we have to take into account that. Of course, you get a plus here. You get a minus here because you get less gas to sell. Plus, you have fuel. And of course, this is a minus here. Okay. Any questions? This is now what is coming out of this is the NGL number, the target, which is NGLs in cubic meters. And local optimization here, what are you going to optimize? If you lower the temperature, you get more cubic meters of NGL. There's not a lot to optimize. Okay. Now there might be lots of considerations when they actually did the design of this. I mean, there might be lots of complicating issues, pressures, compression, who knows what, that are not included in this. This is a very simplified thing. So in reality, we have nothing locally in this discipline, in this model, to really study and optimize. Okay? Okay. Okay. But this number here is the main result, in addition to the sales gas. That's also kind of a major result. So we're going to have to pass that to the economics group, in a sense. Okay. Okay. Any comments before we go on to the economics part? What I can give you is a little more realistic figure with respect to the efficiency. Now, this is the NGL efficiency by component, where the components might be C2 to C6. Okay? Something like that. And what you'll find is that you'll get kind of an S-shaped curve like that. And this will be something like this as a function of your dew point controller temperature. So it actually it is more complicated than what we're saying. So what we're taking is kind of an integrated average of the total components that are being liquefied. Okay.
So basically what it says, if you take, for example, you look at C4 and you take low temperature.
Yeah, the lower the temperature, this might be minus 40, and this might be plus 20. So for C4, you're getting basically all of it out with the low temperature, 95% recovery as a liquid. Here we're getting 60% recovery as a liquid. Here we're getting 25% recovery. And if you go to 80 degrees, then this is just a flat line, because it's at equilibrium. It's an equilibrium gas at 80 degrees C. It's a flash gas, so there's no liquid precipitating out at 80 degrees. But our well stream composition might look like this. You might have 10 mole percent C2, Okay? So the number that we're getting is kind of it's an integrated average. When we go to a single FNGL, it's basically taking the amount of the C2 times the efficiency, the amount of the C3 times the efficiency, and so forth, to come up with an overall efficiency for these NGL components in the well stream. So it's kind of an average. Now, communicating to the process engineers, this is what I want, this is what I need, is not easy. Because these guys, they may not even look at this particular figure. They just run the simulator and it gives them some volume of NGL, and they don't ask questions. But actually, this kind of table can actually be read into Eclipse 300, the compositional reservoir simulator, if you wanted to use that to build the process into the reservoir model. It requires this kind of input, these fractions. So you have to work, the reservoir group has to communicate a little bit with the process group to get from them what they need. That's another part of the integration issue, is getting from the other people what you need downstream or upstream. So it's not easy to get it out of them because they may not understand why you're using it. And if you start showing them an Excel sheet like this, don't even do it, because they'll just they don't want to talk to you. You're a stupid reservoir engineer. But these kind of things have to be built, these kind of approximate models. Okay, so we'll go on to the economics proxy model. And here, this is not my strong suit because I basically don't like dealing with money and don't know too much about it. But I realize that it kind of is the important thing. So I may have forgot some of the key factors here, but we've got gas price, NGL price in dollars per cubic meter. This is in dollars per standard cubic meter. I don't know whether these are realistic numbers or not without converting them to standard cubic feet and barrels. I suppose we should probably do that. If you're not familiar, then we can convert those just to make sure. The gas price should be around $5 per 1,000 standard cubic feet, plus minus. We'll just check that. So dollars is okay, but there's There's 35 cubic feet per standard cubic meter. So there's 0.035 cubic meters per thousand. No. 0.035 MCF per. So that would be that times. That can't be right. 0.0353, 35. What is it? 35.31. Okay, $10 per NCF. That's a good gas price. That's yeah. And dollars per barrel. That would be that divided by 6.28. That's about today's price. So dollars per barrel. So these are, the $10 is high for now. So this probably should go down to maybe 20.25. It's even less than that now in the U.S. So, but probably in Europe these are realistic prices. Dollars. Okay. So then we've got a discount factor, 0.1, 10% annual discount factor. Well base cost, $100 million. That's expensive well. Well diameter factor. This is that factor to increase the base price of a well when you start getting these large well bores. Okay? And that's empirical. I don't know, I've come up with some kind of an equation. Well diameter exponent. So over here we've got somewhere cost factors on wells. This is the, as a function of diameter, this is the multiplier on the base well cost because of a large diameter. And the formula, I don't know what it is, but let's just see what happens if we change this to a smaller diameter. It should translate, see, it's only 14% above it. And if we get wild here on our tubing diameter, then we're going to be penalized. Wells are now costing $500 million. You know, it's just crazy. Okay? But if you try to put that size of a tubing in a well, it's going to cost a lot of extra money. Okay, so that's so the formula for that is the diameter. I'm not sure what this dn is. Now this is a link to the now this is kind of like a normalized dimensionless diameter to get it to go from 0 if you're at 1 inch diameter to 1. It gets big when this gets big. So basically it goes from 0 up to some larger number. 13 inch is the maximum that, so 13 times that. So it's a normalized diameter, and then this factor is that normalized diameter here plus 0.8, I don't know where that comes from, times the base well cost, F10 to the power C. That's yeah. So these are just numbers you can change. The point is that you have to have some cost increase for larger diameter wells. That's the bottom line. And I tried Eck Olson, I tried Sigbjørn Songesland, I've tried everybody, and nobody will give me numbers. Absolutely nobody. You know, if they were forced to make the calculation, let's put 12-inch wells in Ormen Lange, somebody would have to go do the effort to do it. It would take them 3 or 4 months to maybe do it, or maybe 6 months, to come up with that price adjustment for this monster tubing in the Ormen Lange wells.
They don't know. Their coach numbers as soon as they will figure it out.
Yeah. So. But in the meantime, we can build our model with something that's got some realism to it, and then if we show that the tubing diameter has this incredible effect on the development, then you have to go in and refine that. You ask Schlumberger or somebody else to refine that cost model. Okay? But you can do stuff without having that refined cost model. You can't assume that the well cost is independent of diameter. That won't work. And maybe if this factor went to 50, that would be ridiculous. But there's a model for cost related to diameter. Likewise, there's a cost associated with the lower the temperature you run the dew point controller at, the more expensive the dew point controller unit. Okay? So here's a cost factor for the dew point controller. Likewise, a similar equation. And you have a normalized temperature again, and you have these two factors, and that's the model. So basically, if you go to a lower temperature here, or I'm sorry, higher temperature, it should be no cost at 80 degrees. dew point controller 1. The dew point controller base cost, of course that would be stupid to run the dew point controller at 80 degrees and not get anything out of it, but there's still a base cost. That probably should go to 0. Anyway, you go to a lower temperature, minus 40, then the base cost is increased a factor of 4. That probably should go from 0 to 4 instead of 1 to 4. So that's okay. So these are cost factors with lots of uncertainty, but they can be worked out if you really want them. Let's see. So we've got gas and NGL price, discount factor, base well cost, increase in the well cost for diameter, DPC costs, and infrastructure costs. That's basically a platform, subsea, kind of independent of the number of wells, maybe pipeline, whatever it could be. Okay? Is there anything you see that might be missing? As there's no fuel costs here. I don't think I've taken that into account.
Is it second order?
Huh?
The fuel consumption is second order?
Not necessarily. It probably should be included. You know, you can easily burn 10% of the gas. You know.
I made a function of the temperature. Last semester you put the fuel cost as a function of the temperature of the.
That's right. Yeah. So it's missing here. So that's something you guys can improve this with. Yeah. But yeah, it should be in there.
And is it necessary, like, you said also last semester, like, you have to take the C1 out of the stream of the engine?
Yeah.
Is it a demethanizer process?
You know, I've tried to make this surface processing as simple as possible for this. We're not doing flash calculations. We don't know how much methane there is.
If I was putting nitrous, that's what I had nitrous. But always when you said nitrous, my face goes to but it's a demethanizer process that we should take out the C1 before you go to the.
I don't know. Really, it's not my area. I don't do processing.
Put that nitrous on.
Yeah, I mean, what we need is some process expert here, and they can tell us first order, do this, do that, and we put it into our proxy model.
I work with a guy, French guy, and with Pro 2, the guy can take the C1 out just with equations.
Yeah.
I don't know if you can do that in high school, but I have to put a process.
I don't know.
Like a demethanizer, take the C1 out just with calculations.
Yeah,
How do you think they got in the calculation?
Well, with this Pro 2, the guy could take the C1 out. And that's what it's that's use that one. So otherwise you have to use
Yeah.
gas, right?
I don't know. I really just I'm not sure. But like I said, I probably wouldn't pass first year process technology with this. But conceptually, this is what should be done, and you need a more rigorous model, one more on the x-axis with some data, and you can create a proxy model, which is a simpler model, empirical, tabular, whatever, best fit equation. Okay. So now the integration again, the linking of numbers are done. You can see that here we've got the tubing diameter. I'm bringing these numbers over from the other sheets. Okay. Number of wells, dry gas sales, NGL. Okay. And these are volumes, for example, produced at the end of plateau. And I stop all calculations at the end of plateau. Okay? just for the simplicity of it. What comes afterwards is just gravy. Okay, the big money is that we have to deliver to the Germans for 12 years, this amount of gas, and the 12-year perspective, what happens after that's dropping off, so the net present value will reduce its value. So this is good enough for purpose here. So these are intermediate variables, normalized diameter and temperature. This is the plateau length. This is the gas in place. Recovery factor at plateau. NGLs produced. That's one of the key results. Cost factors. These are the total revenues. These are taken by, this is taking the revenue, dividing it by the number of plateau years. Okay. Now, the reason that you have to have this time revenue is to do the discounting of the future revenues with the discounting factor. So we know the total amounts of gas and NGLs produced. We know the price, which I've assumed fixed, invariant in time. So we kind of get the total revenues, and we just distribute those over the number of years plateau. And then on the net present value, you take that vector and you discount it with the discount factor here. And then you have to subtract off the infrastructure cost, the well cost, and the DPC cost. Okay? So you discount the annual revenues, and then you subtract off the infrastructure costs, the well costs, and the DPC costs. The total revenue of gas is simply the total amount of gas that you produce.
Can you write it on the PDF?
Yeah. Okay. So economics, we've got the price of gas is constant. The price of NGL, constant. The volume of gas sales is constant through, okay, and this is only through economics through plateau period. Because the composition from the reservoir is unchanging, again, the NGL rates are constant. So then we get the revenues will be the sum of gas rates per year times the price of gas plus the oil NGL rate times the price of the NGL and then the discounting, see the way it's done here, that's total revenues. Let's see, make sure this is which is the same as the cumulative gas dry times the gas price times the cumulative NGL times the price of NGL. And then the discounted revenue is this revenue from gas, which is this, and the revenue from NGL, which is that. And then you have to divide by 1 plus the discount factor, I think, to the power of, well, something like that. I plus 1, I and a half, you know, whatever you want to do. What do you all like? I think, I don't know how it works. It's, you know, the first year income, it's kind of discounted halfway through or something. Any economist in here? Get all excited about choosing which exponent here? I minus a half, or I don't know. Doesn't matter. We'll just write.
You work on the middle of the year. Start on middle at the end of the year. So it's okay. It's fine.
Okay.
Just to make sure that it's the end of the year. The revenue, the end of year 1. Because if you have cost, you start with I equals 0. Because the investment is in the end of year 0.
Right. So the net present value here, right, will be this discounted revenue minus the cost for infrastructure, minus the cost of the wells, minus the cost of the DPC.
Yeah. That you have to bring to year 0, or to the end of year 0. And you started from year 1, right? Okay.
Right. Yeah. Now, we don't have a fuel cost.
Forget what? We are in Davos.
This is a tax haven, Norway. You live here because you don't want to pay taxes. Okay. Yeah, you know, this is you know, you're getting so far beyond me, I don't even know. Okay, you have factors for royalties, you have taxes, you have God knows what. Okay, I don't want to go there. Okay, but they're all there. Like I said, I don't like money, so I just kind of. But there's enough money here, issues that we can make some. The point is that in a real economic model for a company, they'll have all of the whole tax structure, price escalation, God knows what. Okay. They'll have all that stuff there. They want the product revenues. They need to have some cost dependency on things like dew point control of temperature, well diameter. Those are the kind of things they don't have in their models today that they have to include some way or another in their economic models. Okay, and then I'll just do it like that. Okay, the rest of it, taxes, royalties, the rest of the okay. So in this sheet, you effectively, you know, if you go up in price, you know, back to our point, $10 an MCF, of course it's going to affect the NPV immediately. And if you want to see the effect of discounting, we've got $43 billion net present value, and you don't discount it, and it goes double, more than double. So you can see discounting at 10% over 12 years is a factor of 2 drop in the value. It's a big, big thing. Okay? So now we have an integrated model with all of the key variables that we've decided to include. And if we change any of those variables, we get an immediate response on the net present value. Okay, so now we can start doing something, actually trying to do something in the way of optimization. We can put tubing diameter, a very production engineering-ish, you know, hardware thing, item, directly coupled to the net present value, which in fact it really is, or can be, for gas development. And the way you do that with the sheet that you have is what I call manual optimization. Okay? This is the way I used to talk about the Chinese. I went to China in 1984, and I went to one of their big gas condensate fields on the edge. On the edge, it was like a marsh, and we drove into this town. It was only this gas condensate field. That was all there. I mean, there was a whole town industry around this development. And the first thing I see when we drive into this town is 5.5-inch casing, or maybe 7-inch casing, 7 pieces of casing being pulled by 2 horses. You know, and they were drilling 12,000 feet wells out on a marsh. I mean, it was like this, wow, you know, can they do this? And it's kind of like doing things manually. You don't have to have, you know, big John Deere tractors to have a lot of rice, you know. You just got to have a lot of people who pick it. So this is doing optimization in the manual way. We can go and change any number. We write down the net present value, just go back and forth. So this is my manual. I went in and I decided to have 2 main variables, tubing diameter and dew point control temperature. Okay, and of course I put in inches here just to kind of have a feel. And then I just, you know, wrote down the numbers. Each one of these, this is manual labor here, you know, poorly paid manual labor. And I did it for 4 cases. And then what I did is I put over here, I copied these red cells, a copy and paste special value, so I could come back and say, well, this is my set of assumptions for these manual optimizations. You know, because I end up changing some number, and you know these results won't be valid. You have to document what you're doing. There's so many things you can change. So anyway, this is just a manual. It doesn't, you know, it took 25 minutes yesterday or the day before yesterday. I was just bored and, you know, just sit down and copy and paste. And you create your own assessment of what's the optimal tubing diameter and what's the optimal temperature. And this is something that I want you guys to go through and do. Okay? And the reason for that is because if you go straight to the optimizer, you don't have a feeling for anything. Absolutely nothing. I mean, and when you do optimization, you want to have a feel for what are the main variables that, I mean, the real important ones. Is there a maximum, is there any reason to optimize? You want to do some line searches, if you will, kind of studying this variable, what's the impact on net present value? That variable, what's the impact? And keep everything else constant and just change one at a time. Get a feeling for what you're actually optimizing. Because when you start changing 5 things at the same time, that surface, you have no idea what it looks like. Okay? It's in 5 dimensions. You can't see it. So try to take some cuts through that 5-dimensional surface in 2 dimensions and look and try to understand how in this case, the objective function, net present value, is changing for these key variables. So I want you to pick some variables. I've picked these 2. Maybe you want to pick some other ones. Then once you pick them and make some calculations and tabulate them, then of course you can make some plots. And these are my plots. Okay, and what we see here is that there's clearly a tubing diameter, a maximum, an optimal tubing diameter. That's the one thing you see. And the reason for that is that the larger the diameter, the fewer the wells, right? The lower the cost. So the further you go to the right, you're having less wells, less well costs. So you'd think that the net present value would just keep going up, but it doesn't. And that reason for that is this increase in the well cost as the diameter increases. Okay? And then you can see clearly there seems to be a monotonic optimal towards the minus 40. I didn't run the case. I didn't really study it, but it looks like maybe minus 40 is the cost of the dew point controller is far offset by the additional revenue in liquids. That's what it looks like. I'm not sure. So, I thought that we could let everybody spend an hour. Now we'll choose a different set of numbers so that you don't get exactly the same results as I do. We'll change the problem a little bit. And I don't know if there's any other variables that we want to look at. I mean, we've got we could lower permeability reservoir, change one number. KH changes A. So you can go from this, maybe it's a prolific reservoir, I'm not sure. If you increase or decrease A, I guess if you decrease A, then you're increasing the KH. So you could look at that. B, the tubing, that's already been taken into account with the diameter. You could change gas in place. Period, plateau period, maybe make it shorter, 8 years. What do you think, Mike? Let's put together a different scenario here. We can make it lower permeability by increasing this to 0.1. That's 2.5 times lower permeability. And then we can move to a smaller gas in place. 4. In 8 years. And change the pressure. 60 bar. Okay. And then what I'd like you to try to do is add a fuel consumption that is linear with with the temperature. That you use up to 10% of the available gas as fuel if you're at minus 40 degrees C. If you're at 80 degrees, there's no fuel consumption. Just make it a linear function. So we add some fuel costs. So you basically just get rid of the sales gas. You just factor down the sales gas volume. You don't need to add a cost. It's lost revenue. So let's bring this. Okay, let's.
it's not just a snug Excel to put it in the journal. You can just mark it and copy it.
Yeah. Let's see, should we change anything else here?
Gas price, I think, is probably one of the things most volatile.
Yeah, this is high. Let's make that 25. That's more realistic. I think this is. Okay. What else? Nothing on the process. And then we want to add fuel model, which is that the gas sales times factor for fuel, 1 minus factor for fuel maybe. Fuel factor will be equal to 0 at 80 degrees C and 1 at minus 40 degrees C, DPC, temperature. Just linear or whatever. And we're basically looking at tubing diameter and temperature dew point controller as the key variables here, I think, once again. And I tell you what we'll do here. I'm gonna change this for 8 years. I'm going to move this up to 06. So we still get about 50% recovery at the end of plateau. So I'll change that. Okay, so we'll make it 6% per year for 8 years instead. So it'll be a little bit less effect on the discount factor. Now I'd like everybody to reproduce the kind of tables structure and that manual optimization that I created. I mean, if I can do it, you can do it. Okay? That means filling in the numbers. Okay, running the case, filling in the numbers, like the Chinese. Okay, manually. Of course, they do everything automated now. They're, way past us. And copying on the right side of that sheet these assumptions. Okay, so you know your case. So you can just take the sheet I have and make a copy of that sheet. I'll show you how to do that. You take a right click and you say move or copy. Create a copy. And then put it just below manual optimization. Create a copy. You have to click that. Put it down there. And then that's your number 2. That's yours. Hey. Yeah, if you could open a window here, we'd all have a frick. Limiful. Ahora. Gärna. Tack. So basically, that's
Can you repeat once again what you're doing? How you're doing it?
how I made the copy.
Yeah.
Okay, I'll delete it. Okay, you just take right click, move or copy.
You right click on where?
On the tab.
On the tab, okay.
Okay, you go to the tab and you right click on the tab,
Okay.
move or copy,
Okay.
create a copy, and then where you want to place it, directly after the first manual optimization,
Okay.
or move to end, whatever you want to do. Move it there. I don't care. And then it's created.
Okay.
Or, and then if you want to do it a little easier, you can say, this is Curtis's, and then we'll just fill in this one, right? If you fill in the numbers here, right, and there, and replace all these, then the plot I make will immediately be your problem. You don't have to make a new plot. It's up to you. If you change the one that's called manual optimization, then the plot will be associated. This plot is associated with the original one. Okay, so then you can just change the original one here and. Okay. All right. Okay, so we're going to fix the revenues of gas to use the dry gas instead of this, what it used to be. And then I'm going to add this, this is going to be the, that's not here, maybe a fuel gas exponent in, see what we got, 1. And then this, from the formula here, it should be 1 minus Tn times 0.1. I'll just so I want to, and then I'm going to that's this number here times 1 minus 0.1 times 1 minus Tn and now the colder it gets, probably the higher the fuel consumption, significantly. It's probably not linear. So yeah, I'll just, for the simplicity, I'll just let it be linear. Get fancy here. Okay, so we've got the dry gas produced, price of gas, make that fixed, and then the 1 minus 0.1 times the fuel factor, which is 1 minus Tn, okay. All right, so that's fixed that. Any other people find mistakes in anything else so far? And then we've got, what else was in the problem description? Change the numbers, add the fuel issue, and then just start running cases, I guess. I'm going to get rid of all these. Reservoir production, copy, paste special and values, and then process, copy, paste special and values, and then economics, copy, paste special and values. All right, I'm going to start getting these numbers. So 50 and minus 30. So 50 minus 30. And now, for 50, has anybody started running 50 and minus 30? Does anybody get a net present value of $6 billion? Anybody got a similar number? Huh? 6.06? Yeah? Okay. Okay. Yeah, 50, 75. Hundred. $150. Screwed up somewhere here. Damn. Okay, 300. $250. Okay, well, at least that's what I got, whether it's right or not. I made at least 6 mistakes retyping. You can keep going yourself. Anybody get something similar, more or less? Let's see, the maximum is about 115 billion. The previous was about 23 billion. So what changed to make the net present value so much lower, do you think? Definitely got lower. Huh? Burning the fuel costs. Do you think that was the main thing? Smaller reservoir, less permeability. So we really don't know. I mean, those are the things we changed. So I think that that's it could be studied, but we're not gonna do that now. What would be nice is to find this optimum automatically, okay, with the optimizer. Because as soon as we change something, anything, we have to go back through this process, copy and paste, plot. It's going to get old. You guys are pampered. Do you realize that the industry doesn't do this at all? Because the single change that you make here, tubing size, is an exercise they might look at manually once or twice. I mean, to change the tubing sizes and start trying to do, you'd have to rerun simulation models, you'd have to go back to Prosper, regenerate the tubing tables, rerun the simulation models, pass all the information to the process group. You know, it just doesn't happen. It doesn't happen. So, I don't know, Mike, can you think of any other variables that would be key design variables for this project? I mean, what other items, what other major controllable
I mean, with this simple model, I think we capture everything. I mean, if you start to look at the process itself, you know, and you break that simple process into it, you probably find a lot of variables.
Anybody else think of anything that for this gas development? What probably the pipeline design for this rate with this kind of tubing pressure that we're producing against. You know, if you go to higher pressure, yeah. You lower the tubing pressure, but then add compression cost, both fuel consumption cost and the actual cost of the compressor itself.
Of course, you can the cost of the gas you can index it to the richness or to the caloric value, and you can say the more liquid you extract, the linear it is. And of course, it's not linear. You have a fix, but you can get bonus if it's a rich gas. And if it's in the United States, in fact, you have penalty if the gas is too rich. If the gas goes to home consumption, you cannot make it too rich because the burners in the houses are fixed to a certain caloric value. If you sell it to a power station, you can sell rich because they can change the burners. So even on the product itself, you have a range of bonus and penalties according to the caloric value. We didn't kind of think about that, but we can put another function.
Okay, let's quantify it. You're saying that it's one. Okay, if this is the BTU, the energy of the energy value of the gas. Okay, and let's say this is our reservoir gas here with no processing. Okay, and what you're saying, if it's too rich, there's a penalty. So that means that. So if this is actually being penalized, let's say below 1.
Just to give you an idea, when Statoil take gas from Snorri, liquefied, send it to the United States. If it's too rich, they have to mix it with nitrogen. Otherwise, they are not allowed to sell it. They have to reduce the caloric value.
Okay, so then what we're saying is that it's too rich, it's the lower price. So that means that as the dew point controller, so this in this direction here, we have basically the temperature of the dew point controller, making it a leaner gas, right? We have to make a function of our key variable some way or another. So we have temperature here at 80 degrees and then minus 40. Now as you get leaner and leaner gas, if it gets too lean, then you're also
you get the function. So you have a function
down here. And what you're saying is that this is a non-monotonic function, something like this. That you can be, if you're in the right interval, then you can actually get added value. And if it's too lean or too rich, then you have a decreased value. Okay. See? When they start talking, when they start yabbing, you know, well, this and that, you have to get them down on the ground, sit on them, until they give you numbers. Okay? Otherwise, you can't bring it into the optimization. So now the numbers, Mike. Is it a 50% hit on the price? Is it 80%?
Within 25% on the price.
So that's a scale. Okay, and then here we just have to pick. We can put some model in there. It can be right or, I mean, as long as it's got the character, we put it in there, we see if it has an effect. If it has an effect, then we go out and actually talk to the gas purchasers, and we come up with something that's correct. Okay?
But by the way, just a little comment, you know, all these things, all this behavior, all this distribution, two-dimensional kind of models. And there is a very interesting website called Zoom. Zoom.com. And you get 26 pages of all kind of function, distribution, from biology, from God. You probably will find something that will suit any
Okay.
Zoom.
Okay, so the point is that as soon as someone brings something on the table, you sit on them. Okay? If they can't come with a number, if they can't come with a model, if they can't quantify it, you send them on their way. Okay? Now, of course, if it's somebody who's really saying something that's important, you know it's important, then you can't let them go out the door. You just have to get 2 or 3 guys, sit on them, and then beat them until they get numbers out of their mouth instead of just talking. You know, this is important. This is a factor. People are not used to doing it. They may know it's an important factor. They may know the order of magnitude. All you need is the order of magnitude of the effect and the general correlation. You put it in, we put in a parabola, and then we give a parameter that allows us, you know, to set this if it looks like that, or if it looks like, you know, that, or whatever. You give the capability, then you go refine it, and then it's there. Okay? Model for cost, model for revenue, everything has to be built into it. Any other suggestions about things that could be done on? Alex's comment was that basically we have a 60 bar delivery pressure. Okay? That's going into the pipeline to sales. Down here we've got obviously something lower, okay, at the point where they're taking the gas. Okay? Now, right now we're delivering, and through the pipeline we're losing 25 bars of pressure through this pipeline. Okay? That's a dimensioning effect. You only have 25 bars to lose. So you have to dimension the pipe accordingly because you've got a distance 10 kilometers. So then this diameter of the pipeline is something that, now if you lower this to 25 bar, okay, which might make sense for a very high deliverability, high KH reservoir that has a relatively low pressure initially. That might make sense. Then, to get this to 35 bar, you're going to have to boost this up, okay? And once you're boosting it with compression, then maybe you can get a different diameter pipe, smaller, lower cost, and boost it up to 90 bar. Okay? So now there's an interaction between the compression, both the cost of the compressor, the fuel consumption, how far you boost it, and the diameter of the pipeline. And all of a sudden you get this interconnected model.
That's in fact one of the most interesting things in the gas export system in Norway, because the higher pressure you have in the pipeline, you need more power to compress it, and you have more back pressure, but then you have more capacity in the pipeline for fluctuation in the user. In fact, in the Norwegian gas system, just in the pipeline itself, there may be 2 weeks export capacity. So basically they can shut down the field for 2 weeks before they're empty. And they design. So there is kind of a trade-off. You raise the pressure in the pipe, you get more, you have to compress more, you have more back pressure, but then you can have bigger fluctuation before you have to start to switch on compressor and start to switch on more well. And in fact, there are 2 PhDs just recently were done, financed by GASCO, which is the Norwegian gas export system. We're looking into the relationship between optimization between high pressure, how much you gain by, due to fluctuation, you don't even feel them in the upstream side. And if you go with low pressure, much less to compress. But then each time on the other side they have fluctuation, and then everyone has to put extra compressor. Very, very interesting issue.
Okay.
So that's the pressure. That's the whole problem between Putin and Ukraine. The Ukrainians realize that in the pipeline that goes within Ukraine, they have like 3 or 4 weeks their consumption just in capacity. So they just steal a little bit. And he even doesn't feel it in Russia, taking some time to feel. But that's another optimization issue that in Norway we're looking very much into it. The pressure versus the fluctuation impact on the input. We can find some function for that as well.
Okay, any other, for this problem, which is isolated to a given reservoir, okay, is there any other ideas or thoughts about issues on major design? We've got pipeline design, we've got tubing design, tubulars, basically both of those. Number of wells or...
I think here the number of wells is fixed for this project.
No, we're calculating the number of wells. I mean, the optimum, we haven't even looked at the optimum, but this optimum that seems to be, let's say, 100 millimeters, let's say 125, and so no, 125. You calculate the number of wells. That's what's calculated. As soon as you change that number there, you get a number of wells. So you change that, you get a new number immediately.
You fix the plateau length.
Yeah, that's been fixed here.
Okay.
These are all fixed.
And then the smaller tubing, the more wells.
But
Yeah.
no, but the cost of the wells, if, for example, here is the number of wells increasing, but we didn't include the cost of the well as in this number is increasing.
Yeah, we did. Yeah, the economics.
But it's fixed, I think, right?
No, this number of wells is number of wells is brought from there,
Okay, yeah.
times the well cost, times the markup factor.
Okay.
Yeah, absolutely. So the final optimal is 125. It's 30. It's minus 30. It's probably minus 40 since we can accept that. And we got 40 wells, and we've got a net present value of 16 billion, which should be higher than any of these. Okay, minus 40. 40 wells. That's kind of the optimal design for this field right now. So now the question is, can we do this kind of optimization within Excel? What do you think? We've got 2 variables that we think might, at least 2 variables, we might have more. We have a target cell, this one right here, that we want to optimize. That's our objective. We have this cell and this cell are the 2 cells, at least those 2 we want to use as variables. We can put constraints on them. And in theory, we should be able to run the optimizer to solve this, right? Okay, you guys want to try that? Okay. Okay, so let's try. What we want to do is that we want to. Okay, so now I'll try to do what I asked you guys to do. Okay, so we go into Solver. Okay, and set target. That's this one here, right? And we want to maximize that by changing cells. And the cell I want to change is over here. And comma the number here. Okay. And the constraints we'll wait with. We'll solve it. Oh shit. Adjustable cells must be on the active sheet. That's the answer to your question. Okay. All right, so can't do that. So then we have to come up with a different strategy. So now we have models that are on different sheets. And for optimizer to work, the solver to work, it has to have the objective target, all of the variables, and all of the constraints in the same sheet. That's the requirement. Okay? So how are we going to do that? Well, there's different ways to do it, but basically we have to pick one sheet. So what I recommend, yeah.
During the economics and link this PT and temperature to base one.
Yeah.
That's interesting.
Yeah. So you can pick a sheet. You can pick the economic sheet, this one to be the main sheet for the optimization. But then you have to have basically the, but you have to do it a little bit careful because if you put the, let's say that we put the tubing diameter, I'll just copy the name here, not the numbers, here, okay? Then, well, is there a name? Let's see. And tubing diameter, that should be DT. Okay? There. And now I want to put a number like that. Okay? Now what you want to do here, yeah.
Just define your where do you want F6 and F7 and just make it equal to the value in the economic.
Yeah, that's what I'm saying. You have to be careful because now the 125 is in red is being put here. But you can't do that anymore. So this changes from being red to being black. And then you have to link this to the economics number here. Okay? Only red numbers, input. Everything else is different color. So now that's being fetched from the economics sheet, which is being changed in the optimization here. And we do the same thing for process. We'll copy these two, the text here, and we'll put minus, or we'll put 0. We'll get the units as well. Make all that red. Bold. Okay. And then we have to change this to be black. And then link that to the economic sheet. Okay? Does everybody follow now? You have to have all of the... Now, we did it in the economic sheet now, but my recommendation is the following. That you create a separate sheet for optimization. And the reason I say that is because right now we did it with these two variables, but maybe we want to start adding new variables and all of a sudden you kind of get, yeah. So, you know, it's a little different strategy, but you could have a completely different sheet that's just for optimizer, where you bring in and you actually set in red all those variables that you want to end up changing, and then you fetch the numbers from other sheets that are either constraints or objectives, right, which are being fetched from other sheets. So that's a, but right now this should be sufficient. We've got in the same sheet, we've got the target, we've got the tubing diameter and the temperature, like that. And now we can go back and try again.
So it's such that the variables have to be on the same sheet, but the logic and the function relationship
can be elsewhere. Yeah. So the variables, they have to be on the same sheet as also the constraints and the objective.
Is that has to do with the reader of the
it has to do with just, it's a requirement. You can't do it in, I mean, it's just solver's requirement. Okay. Okay, so we go into solver, and now we have this as our target. We want to maximize this net present value, subject to the two constraints here. Mohammed, you asked how to put in 2. You can do it this way if they're next to each other, but you can also do it this way. You can just say this, and then click on the next one. This one, comma, and that one. That's allowed. Okay. And the constraints, we want to go ahead and add those. Probably makes sense. So we'll say that, oops, that was not right. Add constraint, we want to have this less than or equal to, what did we agree on, 300? I think, realistically. And add it. This one greater than or equal to McDonald's straw. Temperature, add less than or equal to 80. And, okay, change the objective. Okay. And then add this greater than or equal to minus 40. Okay. And then close, save, just safety, and go back in, solver, and then solve. Bang, 117. And we need units here. And 80 degrees. Now, does that make sense? Huh? Okay, so let's start at, Shinazana saying that, this solution doesn't look right because we got 15.8 here, but if you go to minus 30 here, it's lower. Now, something doesn't seem right, compared with our plots, at least. Minus 30 has got the highest net present value. So what's going on? Picking it up right. If we go to manual optimization and we just pick minus 30 and let's say 100, 100 and minus 30, we should get a net present value of 1447, and that's right. So did you ever find, okay, but it's driving us to 80 degrees. Starting from here? Okay. Ah, cool. Okay. All right, I like this. Yes. Okay. It don't work reliably. Okay? It don't work reliably. Meaning that you have to do some engineering. It's not just like point, click, and you're there. Those are always the funnest problems. So now you guys do just what I did. Set up the solver in so that you have the links wherever you want to do it like this, or you want to create your own sheet. Get all the variables, target, everything on the same sheet, and run the solver and start trying to figure out how many local minima there are, or maxima. Okay? Start studying the problem. Initial values here take me to this wrong solution. Initial values here take me to the right solution. Okay? Start getting a picture of what the surface. I'm a little bit surprised that there are local minima. There obviously are. Okay? Get to work. That's nice. Good. It's definitely not convex. We don't need to check that. Okay. But I don't know if we can see. This is where Bjarne can say, well, we could go in and look at the output of this and that. We could see that it's not convex. I don't know. I'm not sure. But the bottom line is, you've hit the solve button. It says converged, feasible solution. What feasible solution means is that it satisfies all the requirements. It finds the maximum, but it doesn't say global maximum. Okay. It's very interesting. It'd be nice to make a surface, a two-dimensional surface of this, to see these local minima. Because you don't see it from this plot here. It doesn't. It's kind of strange. Interesting. Minus 30. Yeah, so I think I can see the problem. Now, I didn't realize this was non-monotonic. I didn't pay attention to the plot here. But what you see is that if you plot along a line here, which is not the optimum but close to it, you see that the net present value at minus 30 is up here, and the net present value at 0 is down here, and the net present value at plus 30 is up here. Okay? So what happens is if you start over here, it's going to, it appears that there'll be some other maximum, maybe not a maximum, but it'll hit the browns at plus 80. That maximum is still lower than the maximum here, I think. I haven't really tested the solution, but probably this one's higher. And if you start on this side of about 0, it looks like it'll take you to this false local maximum over here versus going to this one. Okay? This temperature here is what we call the radius of convergence for this solution here. Meaning that if you start on this side of it, it'll converge to this solution. But if you start on the outside of that radius, relative to that solution, then it'll take you to another solution. Now it's an interesting problem because the net present value at these two solutions look quite close. Yeah? Is that right? Let's just find both solutions. This is 117, 1.587. Okay, so at diameter tubing of 117 and temperature dew point controller at plus 80, we get a net present value of 1.587, 10 to the 11 US dollars. And then if we rerun it with starting at minus 10, should take us to another solution, yeah, which is also 117. So that optimal doesn't seem to be on the diameter at all dependent on anything else. So that's that dew point controller minus 40. And this gives a net present value of 1.598. Okay. Now it's a very interesting situation. If you say, oh well, we're going to make an extra $0.02 billion, well, let's go for the DPC unit. But you know that doesn't make sense, does it? That major investment, maybe the platform has to be larger because of the unit, more uncertainty. You know, I mean, there could be lots of other issues that basically you've got two solutions that are almost identical in value, one with definitely less investment up front. So I don't know.
So, I mean, you're not interested only in the absolute optimum, but how it approaches the optimum. It's a very flat function, then you don't care about being...
Yeah, well, that's true, but on the other hand, this is really not that flat. I mean, it is kind of flat along here. I mean, but you know, this is a $0.2 billion. I mean, it's, you know, there is a difference here from minimum to maximum, but from the two optimal, doing nothing and doing the dew point controller, there the values are almost the same, and then you have to start looking at other criteria. Do we really want that huge, you know, processing facility there? Maybe you think in the future there are other fields that will come in, and that dew point controller can be a big asset further into the future. So you kind of end up with two equally, basically the same value there. But really one is do it and do it completely, and the others don't do it at all. So it's an interesting...
you have you start to put some weight factor, in the optimization. That a few things, you just give lower priority. I don't know. I mean, increasing the dew point plan looks more complicated than increasing the tubing, and maybe you can play with that. I'm not sure.
I don't know. I mean, it's definitely there's other. I mean, the pure mathematical solution says that these are basically equally good, optimum, which is kind of an unusual. Yeah.
Then we have to consider another economic parameter like return rate.
Rate of return could be brought in. You can, probably risk. Risk is maybe you have to start looking and seeing. If there are risks involved. In this case, the dew point controller is no big risk, but it's definitely a big investment up front. I don't know. I mean, there are other factors that come into play now. It's certainly not an intuitive result. I wouldn't have ever thought that, doing nothing and doing the full-blown. You would have thought, at least my intuitive would have been that, there's either some optimal condition of the dew point controller or not, but this doesn't seem to show that.
In the oil industry, at the end of the day, what we decide is what the company feels more comfortable with. If they're never done to a big tubing, they probably will not do, and they'd rather go to a...
But the tubings here are the same, because that seems to be independent of the other. I mean, it seems clear that the optimal tubing is around 115. For this set of conditions, it's much more on the temperature. Was anybody not able to do the optimization with solver? Yeah.
My basic problem was that I didn't catch up with some of the early changes you made.
Oh, okay.
I was going to ask you if you could maybe focus it on that connection with
Yeah, is everybody in the class on It's Learning for Mike's course or not? Okay, so we can do that. Yeah. If you're not, then you just need to let us know, Mike. I probably need to be on your course also, and then.
Yeah, I put you
Yeah.
on the course.
Okay. 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 I think I don't know whether there are any other issues or questions that people have on this. It's definitely not a convex problem, but it's not a problem. Mike, any comments? Anything left? Or questions? Okay. Now tomorrow what we're going to do is that we're going to return a little bit to the 5-well problem, but we're going to go to 60 wells, look at some more issues about the solver, problems you can get into, things like we saw today. It makes it a little more interesting problem. And then we're going to introduce some ideas about if we want to do the same kind of model integration and optimization, but outside of Excel, how do we do it? Okay, what are some of the requirements? What are we going to do? And then we'll look at an example or two using a software platform like Excel, but where instead of individual cells, you can actually launch applications, okay, and connect all these applications within that workspace and do optimization with a more advanced set of models. Okay? So we'll look at that tomorrow as well.